Okay, hello everyone. This is going to be the video for Project 5 Part 1 and 2. So part 1 and 2 are very similar, so I'm going to teach you how to do Part 1, and then you can replicate the same thought and then just do pretty much the same thing for Part 2. So the first thing, I know you guys didn't have a template, so I just came up with a really quick version of a template. So the first part, we're going to have your S1 our model. So if we go to the PDF, is here. So the S1R behavior. For this part, you should have two plots. The first plot is going to be the plot of the S and I population. The second one is going to be a plot in which you have four curves after varying R naught and I naught. Then for the SZR model, we're going to have again an S and C population plot and then a final population of zombie plot. In the next part, we're going to have our Gillespie algorithm and then an average behavior code, and then at the end you should have your two functions. So the first function is here what he gives you, so du dt equal si rode u r naught and n, and then the second one is sc rode, and then we have u alpha and n, so the same thing that was given in the PDF, and this is just our template. Now if we go to the first model, which is the SIR model, basically what we're going to be doing is we're going to be modeling equation set number 2, in which we have the change in ds and then the change in di as a function of this constant r naught and of your two variables, which are s and i. So if we look at this, we have a set of two ordinary differential equations that have two different variables. So basically, what we're going to do first is we're going to make a function that makes this system that has two differential equations and two variables, we're going to make it a function that only has one variable, u, and then t. And then, of course, it depends on your two constants, which are r naught and n. If we look here, you have r naught and n, and then the rest are just your variables. So the first thing, this function is going to be very similar as what we've done in the past. So the first thing that you're going to have is you're going to make your u variable. Your u variable is going to be a matrix with two columns. The first column is going to represent your s variable, and then the second column is going to represent your I variable. And we're going to do this so we can solve both of them simultaneously. So similar as what we've done before, we're going to say that S is equal to U1, right? And then we say that S is, and then I is equal to U2. Then the next thing that you have to do is we have to say, so if u is equal to s and I, then du dt is equal to ds and di. So the first thing that we have to do is say, well, what is ds dt? And for ds dt, you're going to copy down this equation, right, depending on r naught, s, I, and n. And you can just write it in terms of s and I because we already told Matlab where s and I were instead of u1 and u2. So write ds dt as a function of s, I, n, and r naught. Then do the same thing for di dt. Again, write this equation you have here. And then the next thing you have to do is to, so far we've created s, I, ds, and di, but we haven't created du dt, and that's what has to come next. So du dt is just the derivative of u. And if u is s and I, then du dt is ds and di. And you need two columns. So the first column is going to be ds dt, then you put a semicolon, and then you put your second column, which is di dt. And that's how you make du dt. Now when you work on part 2, you're going to do the same thing for your function here as we did before, except that instead of having these equations here, we're going to have these equations here, but otherwise it's the same train of thought. Now we're going to go, so now we know that we're modeling these two differential equations. Now we're going to go down to the question. So what the question is asking us is first to write the function, which we already did. Now we're going to say that n is equal to 400, which is here in my template. It says that r naught is equal to 8, which we're going to just type down. Then we say I naught is equal to 1. So if we have an initial population of humans that is 400, right? And then one of them becomes infected, the population of the healthy humans is just going to be always the total number, which in this case is n, which is equal to 400, minus the infected number. I know some of you had questions about that. So S naught is just going to be your 400 humans, so n, minus your infected humans, so I naught. So the sum of these two should be the total number of humans you have, which is 400. So now that we have our two initial conditions, so now we have n, r naught, I naught, and then of course we need s naught because we're solving two differential equations, ds and di. Since we have two differential equations, we need two initial conditions, which are I and s. So something that you have to take into account is that since we're making s u1 and I u2, we have to stick to that order. So when we're writing down the initial conditions inside the ODE, the first one has to be the initial condition for S naught, and then the second one for I naught, and then correspondingly. So the next thing that we want to do is we say we want to actually do ODE 45 and use these initial conditions to plot S and I. So we're going to do this the same way we've done before. So now we have a du dt, but remember that du dt in this case depends on u, r naught, and n. And remember that our equation that we use in the ODE 45 can only depend on u and t, du dt. So we have to make du dt only depend in u and t. And now, since we already specify what r naught and what n are, this equation is really just depending on u. So same thing as we've done before, we're going to create a function, say conf1, and it's going to be an anonymous function as a function of t and u, and it's going to be just your SIRODE. So basically we're just making a new function and we're going to call it, and we're going to say t comma u, but it's just going to be your SIRODE, so you can just have your SIRODE blah 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 here. So that's your anonymous function, same thing that we've done before, as you can tell. Now the next thing you do is, of course, solving your differential equation. So you do t comma u, not mesh, okay, t comma u, and then we're gonna do the same exact way we've done before. We do ODE 45, then we open parentheses, we know that the function goes first, which is our fun. Then our time span, we go here, and professors wants us to plot from 0 to 10, so our t span is of course from 0 to 10, and then we want y naught, which is n minus 1, which is s naught, and then I naught. And that's it for our t comma u. In this particular project, we don't need any conditions, so you can just do that. Now the next thing that we want to have is just the plot. And that's the only thing that is going to go into our SIR model. Remember to add your labels and your titles. Now we're going to do to the second part. The second part says start a new plot. So that's why I put a clear figure here. And we're going to have it in a new section as well. And it says start a new plot, still with n equals 400. So we're not going to change n. I naught equals 1. So we're not going to change I naught. And we say solve the model for r naught equals 0.8, 0.9, 1, 1.1. So you see it's just from 0.8 till 10 r naught. In each case, you should get the solution for at least 2000 t values. So I'm going to teach you how to make this r naught vector and also how to make sure that your solution has at least 2000 t values in an interval from 0 to 20. So having 2000 t values doesn't mean that you're going from 0 to 2000. This means that between 0 and 20, you're going to have 2000 points. And then we're going to find what the value of I is at its maximum. So basically, we're going to run again the simulation, or run the model, and we're going to see how the population of infected people and the population of healthy people change as a function of time. Then what we're going to do is we're going to ask Matlab to find what the maximum of I was through the whole time. What was the maximum number of infected people? So to begin this part, we're first going to make our R naught value. So again, as you noted here, it goes from 0.8 to 10 with steps of 0.1. So in order to do that, we're gonna, I think we've done this before. So for example, imagine I wanna make an R naught value. That goes, so from 0.8, and then we're gonna say, okay, then we put the step size. As you see here, the step size is 0.1. So you write your step size, and then you tell when do you want to end, which is 10. So it's 0.8 step size, which is 0.1 in this case, and then 10. Let's make an example. For example, if we want to go from 0 to 1, and we want a step size of 0.1, then we will say 0, 0.1, and 1. And what this is going to make is going to make, let me just show you. Oh, let me get rid of this. Say outputs. So it makes a vector of numbers from 0 to 1 with step sizes of 0.1. So 0, 0.1, 0.2, same thing that you're going to do here, but from 0.8 to 10. The other thing that is going to come handy is when you do this, you don't necessarily know right away how many points you're going to create because you're just giving it a step size. If we want to know how big this vector is, we can use the command length. What this is going to do is it's going to tell us how big this vector is. In this case, 11. So if we want to loop through each one of these R naughts, we know that we need 11 iterations. So we need a loop that goes from 1 to 11. And we're going to need this now. So create your R naught value. Then what we do next is we are going to say, we're going to create a for loop that is going to do the iterations for us. So what you could do is just literally run it one by one with the different R naught values, but these are going to be many R naught values. So I advise you to do a for loop, and we're going to have a for loop that goes from 1, all the way till the length of R naught. So then you can take advantage of this notation I showed you before, which is length R naught, and then tell the for loop to go from 1 to R naught. And that's how many loops you need to have, because we're going to loop through each one of the R naught values. Now inside the loop, what you want to have is you want to state again your function and then state again your differential equation. So you can just copy your function here and your differential equation. And you want to restate them because you're changing the parameter R naught. So you want to reevaluate what your function is. However, the only thing that's going to be different is your time span here. So before, our time span was from 0 to 10, I think. And now our time span is going to be from 0 to 20, but you want 2,000 points. So you're going to use the same notation. So if you want 2,000 points from 0 to 20, you need a step size of 0.01. So basically, if I do 2,000 over, or 20 over 2,000, number 20 over 2,000, we get the step size of 0.01. So basically what we're going to do is we're going to create a time vector if you want, and your time is going to be, or you can just type it in your ODE. So you do your function and blah, 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 and when it comes to your time span, what you can do is you can just say, okay, so I want my time to start at 0, have a step size of 0.01, which is what we just created, and then end at 20. And then you can write this for your time inside your ODE. So the only difference from here to here is just you're changing that time span. Next thing you have to do is you have to have your maximum number. And again, we're going to be finding the maximum number of I. Remember that U is going to be a matrix that has two vectors. The first vector is S, the second vector is I. So again, if you have a U matrix that is, for example, 1, 2, then 3, and 4, then this column 1 and this first column would represent S, and this column would represent I. If you want to find the maximum number of a particular column, you can use the function max. However, if you just say max U, what it's going to do is it's going to find the maximum of both of the columns, and you don't want that. What you want is to find the maximum number of your second column, which is your infected people column, right? So what you do is same thing as we've done for previous n functions. We do U colon, which means look at all of the rows, and then we tell it, but look at only the second column. and then this just gives us 4. So we're finding the maximum of the second column, which represents the infected people. So you can do the same thing here. However, since we're looping and we want the maximum number for each R0, then what I would advise you to do is just to have a new variable called, for example, max I, and then make that as I. So every loop you go through, you're saving your maximum number in I. And then you can go ahead and put this max function here. So every time you loop, you find the maximum of these are not condition, and then you save it, and then it goes through the next one, and then the next one, and the next one, and then that's all you have to do. Now, outside of this for loop, what we want to do is we want to plot it. So what they want us to plot is, if you go here, is they want you to plot R0 in the x-axis, and then you want to plot your maximum I, which is your max I, over n. So plot R0, comma, your max I over n. I'll show you how your curves are supposed to look maybe at the end of this video. Now, it also, after you've done this, if you keep on reading, it also wants you to loop through repeat this by doing it for I0 20 and I0 50. So what you can do is just, for example, we say I0 equals, so the first I0 that we wanted was the same one, so 1. So then what you can do is you can either do a nested for loop and then loop through your I0, which are only 3, so you would have an outer loop. Or what you can do, okay, let's put the plot here just so you know it goes here. Or what you can do is just copy and paste this and then paste it 3 times if you're not very confident with nested for loops. And then the only thing that you have to do is just change your I0 value. So the first one was 1, but then the second one is 20, and then the last one is 50. If you feel comfortable with doing a for loop inside another for loop, I would do that instead. It's just a lot simpler code. It's going to look a lot shorter. Let's see. Don't forget to put mistakes that I've seen. Don't forget to put a hold on here. So do plot R0, comma, max I over n, but then put hold on, so that every time you do your I0, you get you plot over the same graph. So basically we want a graph. At the end of this section should have a graph, only one graph with 3 plots, one for every I0, only 3 plots, okay? 3 curves. That's all we want for part 1. Now for part 2, you're gonna do very similar things. You're just gonna be looping through alpha instead of looping through R0, which is very reasonable. It's almost the exact same thing. And we're not gonna loop through I0, so it's just gonna be this part here. You're not gonna have to have a second loop. Your one loop is gonna be enough. So it's actually part 2 is a lot easier. It's just make sure you're using the new equations, which are the SZ equations instead of the SI equations. And that's it. That's all you have to do. Please let me know if you have any questions. Oh yeah, I'm gonna show you how the graphs are supposed to look, so that you have an idea.